Our understanding of the world has evolved to help us survive, rather than provide a complete picture of reality. Therefore, it's often challenged by strange situations that don't make sense. These contradictions and impossible events are called paradoxes. Today, we're going to discuss some of the most mind-boggling paradoxes that remain unsolved. In 1950, while having lunch, Italian physicist Enrico Fermi asked a simple yet profound question: where is everybody? This question led to what we now call the Fermi Paradox, which wonders why we haven't seen signs of alien life despite the vastness of space. Our solar system, with its young star and life-supporting Earth, is quite new compared to many ancient stars in the Milky Way. Given the potential for advanced civilizations to develop the ability to travel between stars, it's puzzling that we haven't been visited, or at least found evidence of such visits. Some scientists argue that the Fermi paradox isn't really a paradox. They refer to the Drake equation, a formula created by Frank Drake in 1961, which estimates the number of detectable civilizations in our galaxy using 7 different factors. Early estimates suggested millions of Earth-like planets, but our knowledge of planets around other stars was very limited back then. Recent discoveries have changed the game. By 2020, data from the Kepler Space Telescope revealed that there are over 300 million worlds in the Milky Way, with conditions similar to Earth. About half of the sun-like stars in our galaxy have rocky planets in their habitable zones, and planets actually outnumber stars. These findings have made the Fermi paradox even more intriguing. Next in our list is the grandfather paradox, which has puzzled scientists for many years. Imagine you have a time machine and decide to travel back to when your grandfather was young. For some reason, you take him out before he has any children, including your parent. Now here's the tricky part. If your grandfather dies before your parent is born, how can you be born to go back in time and take him out? This is the grandfather paradox. It's a situation that doesn't make sense because it creates a loop. You can't exist if your grandfather never had children, but you need to exist to go back and take him out. In our normal experience, causes lead to effects in a straight line. For example, if you decide to bake a cake, which is the cause, you mix ingredients and bake it, which is the effect. But in the grandfather paradox, the cause, taking out your grandfather, leads to an effect, you not being born, that cancels out the cause itself. This is called reverse causation, where the effect eliminates its own cause, creating a logical puzzle. If you never exist, you can't go back in time to take out your grandfather, which means he wouldn't have died, so you would exist, and the cycle continues. Let's look at another version of this paradox. What if you travel back in time to take out baby Hitler? Imagine you succeed in this mission, and Hitler never grows up to start World War II. The problem here is similar. If baby Hitler is taken out, he doesn't cause the terrible events of the war, so there would be no reason for you to go back in time to take him out. Again, this creates a loop where your actions in the past remove the reason for those actions. These paradoxes lead to interesting ideas about how time and the universe might work. One popular idea is the theory of infinite parallel universes. According to this theory, when you go back in time and change something, you don't change your original timeline. Instead, you create a new alternate universe where your changes take effect. This way, your actions only affect this new universe, and the original timeline stays the same, avoiding any paradoxes. Another idea is the universe's self-preservation theory. This theory suggests that the universe somehow prevents actions that could create paradoxes. For example, if you try to shoot your grandfather, the gun might jam, or you might miss. Or if the shot is fired, the person who dies might turn out to be someone else, not your grandfather. This way, the timeline remains consistent and you continue to exist. The Bootstrap Paradox is a strange concept in time travel, where something exists without ever being created. It raises the question, how can something taken from the future and placed in the past exist? Here's what I mean. Imagine you are a time traveler. One day, you buy a copy of George Orwell's 1984 from a small bookstore. You decide to travel back to London in the late 1940s, the time when Orwell was alive. You meet Orwell and give him the book. He reads it and decides to write it as his own work. Years go by, and 1984 is published, becoming a famous book about a dystopian future. Copies are printed and sold all over the world. Eventually, one copy ends up back in the same bookstore where you first bought it. This brings us to the heart of the Bootstrap Paradox. Who actually wrote 1984? Was it Orwell, or was it you, the time traveler who gave him the book? The black hole information paradox arises from the clash between quantum mechanics and general relativity. The problem suggests that when something falls into a black hole, its information could be lost forever. But quantum mechanics says information can never be destroyed. Imagine melting two ice cubes, one a sphere and the other a cube. As they turn into water, you can't tell which water came from which shape. However, small differences in how they melt and the shape of the remaining water retain some clues about their original forms. This shows that, in quantum mechanics, information is never entirely lost. Black holes, on the other hand, consume matter and emit energy known as Hawking radiation. This radiation is uniform and doesn't seem to carry any information about what the black hole has swallowed. This suggests black holes might erase information, which conflicts with quantum mechanics. The big question is whether black holes really destroy information, or if some escapes when the black hole evaporates. This paradox isn't fully solved. In ancient Greece, Zeno of Elea came up with 9 paradoxes that have puzzled thinkers for ages. Among them, the dichotomy argument, in particular, challenges our basic understanding of motion. Zeno's dichotomy argument starts with a simple idea. To reach any destination, you first have to get to the halfway point. Imagine you're running a mile. Before you reach the mile mark, you must first run half a mile. But before that, you have to run a quarter mile, then an eighth of a mile, and so on. This sequence can be divided infinitely into smaller and smaller segments. As you think about this, you realize that the remaining distance can be split endlessly. To reach your goal, you need to complete an infinite number of steps. But how can anyone complete an infinite number of tasks in a limited amount of time? Zeno argued that it's impossible, and therefore, moving towards any destination is theoretically impossible. This argument goes further. Think about the beginning of your run. The same infinite division applies. Before you can even start running the mile, you must cover the first half of the initial segment, and then half of that half, and so on. This backward division suggests that starting the motion is also impossible. According to Zeno, this means all motion is an illusion. Centuries later, the Greek philosopher Diogenes the Cynic offered a famous response. Upon hearing Zeno's argument, Diogenes simply stood up and walked around, supposedly proving Zeno wrong by showing motion. While the story might not be entirely true, it highlights an important point. Despite the theoretical paradox, we see motion happening all the time. Zeno's paradoxes, however, are more than just simple puzzles. Diogenes' demonstration, while clever, did not solve the underlying problem in Zeno's reasoning. Philosophers and mathematicians needed to find the exact mistake in Zeno's arguments to truly refute them. This challenge sparked deep discussions and further exploration into the nature of mathematics and its connection to the real world. Zeno's paradoxes have had a big impact on the development of math and philosophy. They led to the creation of calculus by thinkers like Isaac Newton and Gottfried Wilhelm Leibniz. Calculus, which deals with infinite sequences and limits, provided the tools to solve Zeno's paradoxes mathematically, showing how an infinite number of divisions can add up to a finite whole.